Hi students, myself Mohammad Nader. Welcome to a new session of electrical drives and control for automation. In this session, we will have a discussion on the topics torque developed in a DC motor, losses in a DC machine, condition for maximum efficiency in a DC machine, power stages in a DC generator, and power stages in a DC motor. Before going into the torque developed in a DC machine, let us have a look on the basic concept of torque. Torque is defined as the turning or twisting moment caused by a force about an axis of an object, and it is measured by the product of the force acting on the object into the radius at which the force acts. That is, the torque developed, it's an example of a pulley of radius r. If a force F is applied on the pulley, then torque developed on the pulley by the force F is F into the radius of the pulley. That is, torque is equal to F into R, and unit is Newton meter. Then work done by this force in one revolution of the pulley is F into distance. What is the distance covered in one revolution? That is the circumference of circular motion, that is 2 pi r. So work done by this force on one revolution is F into 2 pi r joules. Then what will be the total power developed by this pulley? Total power developed is equal to total work done divided by time. Work done per unit time is our power. So work done for the complete number of rotations is equal to work done per revolution into total number of rotations all by time. As we know, total number of rotations per time in second is rotations per second. We know n is the rotations per minute of my pulley, then rotation per second is equal to n by 60. So P is equal to work done per revolution into n by 60. So P is equal to F into 2 pi r into n by 60, where F into r we know that it is torque, and 2 pi n by 60 is omega, that is angular velocity in radians per second. So P is equal to T into omega. It is the general equation for power and torque. Now let us move on to armature torque of a motor. In a motor, when we give electric supply to the both armature as well as field winding, as we know the basic working is whenever a current carrying conductor is placed in a magnetic field, it experiences a force. Due to that force, my armature starts rotating. So this armature will have its own power. That power is transferred to the shaft, by which we transfer this mechanical power to the mechanical load. So we have mainly two powers. One power is power developed by the armature, and there also torque is developed by the armature. Similarly, this torque or this power has to be transferred to the shaft. Then a torque is developed in the shaft is called shaft torque, and a power is developed in the shaft. Okay. Now let us have a look on the power developed in the armature. As we know, let TA be the torque developed by the armature of motor running at n rpm. From the basic equation, we have that power developed by armature, that is P is equal to T omega or T into 2 pi n by 60. Here PA is equal to TA into 2 pi n by 60, unit is watts. But also we know that the electrical power developed in the armature is converted to mechanical power. What is the electrical power generated in the armature or produced in the armature? EB into IA, that is back EMF. Back EMF into armature current. The EMF produced in the armature into current flowing through the armature will give the power developed in the armature, that is PA is equal to EB into IA, which is equal to the TA into 2 pi n by 60. So let us equate equation 1 and equation 2, then we will get TA into 2 pi n by 60 equal to EB into IA. But we know that from the EMF equation, back EMF EB is equal to phi ZPN by 60A. So TA is equal to 2 pi n by 60 equals phi ZPN by 60A into IA. By cancelling out the common terms, we get TA equals 1 by 2 pi into phi ZP IA by I, where we know that phi is the flux per pole, Z is equal to total number of conductors in the machine, P is the number of poles, IA is equal to armature current, and A is the parallel path. And 1 by 2 pi equals 0.159. So TA equals 0.159 phi ZP IA whole by A. It is the equation for armature torque developed in my armature. So from this equation, we can conclude that TA is proportional to phi IA because 0.59 Z, P and A are constants. So only variables are flux and armature current. So TA is proportional to phi IA, and this conclusion is very important when we move on to characteristics of a DC motor, and we will have a discussion on that topic in the next session. And now let us move on to the shaft torque. As I said earlier, a power will be developed in the shaft when it is connected to my armature, by which we connect my armature to my mechanical load. So a torque will be developed in the shaft, and a part of the armature torque will be required to supply iron and frictional loss in the motor. So the torque developed in the armature torque will not be fully utilized in the shaft, and small amount of torque will be utilized to supply iron and frictional loss in the motor, and losses will be discussing in the upcoming slides. And what will be the motor output? As we know, output power will be equal to torque into omega. Here shaft torque into omega. Omega is 2 pi n by 60, where n is the rotation of my DC motor in RPM. So shaft torque can be written as TSH equals motor output in watts divided by 2 pi n by 60. The unit is Newton meter, and TSH equals 9.55 into motor output by N, and is written in Newton per meter, Newton meter. Now let us move on to losses in DC machines. There are mainly three types of losses. One is core loss, then winding loss, then mechanical loss. Core loss is the loss that is occurring in the armature core of the DC machines, and it is also called iron loss because most of the core of the armature is made with iron commonly, so it is called iron loss. And winding loss occur in the windings of the DC machine. Which are the main windings in DC machine? Armature winding and field winding. Whenever current flows through a resistor, there will be I square R loss, and that is the copper loss occurring, and it is called winding loss, and which will be discussed in detail. And third loss is mechanical loss. They are frictional loss and windage loss. Now let us move on to core loss, which is also called iron loss, since the core is made up of iron, and it is also called magnetic losses. This is the loss that is occurring in the armature core of a DC machine. The two types of losses, two types of core losses are hysteresis losses and eddy current loss. Now let us have a look on hysteresis loss. Okay, as we know, in DC machines, our armature rotates. Whenever my armature is rotating, every portion of its core, every portion of its armature core passes under north and south pole alternatively, thereby attaining south and north polarity respectively. As I said, whenever my armature is rotating and passes through north and the south pole, and a polarity will be developed in the armature in such a way that when it passes through North Pole, a South Pole will be developed in the armature core. Similarly, when it passes through the South Pole, a North Pole will be developed in my armature. Thus, it is understood that the core undergoes one complete cycle of magnetic reversal after passing one pair of poles. That is, when it passes through one pair of poles, my magnetic field gets reversed. That means my core undergoes one complete cycle of magnetic reversal when it passes through one pair of poles. Now let us look what happens when there is a magnetic reversal in the armature core. Before that, every magnetic material has a basic component called magnetic domains in it. Normally, these magnetic domains are randomly arranged, and when we apply magnetic field to my magnetic material, these magnetic domains which were randomly arranged will get aligned along the direction of magnetic field. So, as I said, here there is a magnetic reversal when it passes through one pair of poles. So what happens? Suddenly there is a reversal of magnetic field. So my magnetic domains should suddenly change its direction from previous north to south from south to north. In this case, as I said, when it passed through north pole and south pole, correspondingly south and north pole will be developed in my armature core. So magnetic reversal takes place. Whenever magnetic reversal takes place, my magnetic domain should suddenly change its direction in order to align with the new magnetic field direction. So it requires some energy to change its direction, and there will be a power loss when it utilizes this energy, because these magnetic domains are utilizing the energy that we required in the output for changing its direction. Thus, a power loss will occur in the armature core due to the magnetic reversal, and that power loss is caused by the direction change of my magnetic domains, and that loss is called hysteresis loss. And Steinmetz has developed an equation for hysteresis loss, and hysteresis loss is equal to eta into B max raised to 1.6 into F into V, where eta is the Steinmetz hysteresis coefficient, and B max is the maximum flux density, F is the frequency, and V is the volume of the core in meter cube. So I can conclude that hysteresis loss is directly proportional to B max square into frequency. The next part of the core loss is eddy current loss. As we know, whenever my armature core rotates, it cuts the magnetic flux. As we know, we want EMF to be generated or induced in the armature windings only. But whenever my armature core is rotating in a magnetic field, according to Faraday's law of electromagnetic induction, an EMF will be induced in the armature core. Even though the induced EMF is very small, my armature core area is very large. My armature core area is very large, and as we know, resistance is inversely proportional to area. R is equal to rho L by A. Since resistance is inversely proportional to area, due to large area of armature core, its resistance is very less. Due to its very low resistance, very large current flows through the armature core, and this current is called eddy current. When armature core is rotating in a magnetic field, a small EMF is induced in it. Due to low resistance of armature core, a very large current will be produced in the core, and that current is called eddy current. Actually, we do not require this current because we want current to be induced in the armature winding only. So this current is a loss for us, and the heat developed by this eddy current will be considered as the loss of my machine, and the power loss due to the flow of eddy current is called eddy current loss. To reduce this eddy current loss, what we have to do? We have to increase the armature core resistance. How can I increase the armature core resistance? For that, I will laminate my core. And for lamination, what we do is the armature core is divided into thin circular discs which are insulated from each other. Each circular disc, thin circular disc, are separated from each other by insulation. Thus, core area is reduced. When core area is reduced, what happens? Resistance increase. When resistance is increased, the eddy current produced will be a lower value. Thus, we can reduce the eddy current loss. Eddy current loss W is proportional to B max square, F square, T square, V square, where B max is the maximum flux density, which is expressed in Tesla or Weber per meter square, and F is the frequency in Hertz, and T is the thickness of the lamination, and V is the volume of the core. Hope it is clear for you. The main important point in the core loss are core loss always depend on the voltage applied across my machine, or voltage across my machine, or voltage across my armature. Since this voltage is almost constant, our core loss will be always constant. Core loss or iron loss, that is the sum of hysteresis loss and eddy current loss, and that loss will be always constant. Now let us move on to winding loss. Winding loss, it is also called copper loss because most of our windings are made of copper, so it is called copper loss. And as we know, both the armature and field windings have their own resistance, Ra and Rf respectively. Whenever current flows through a resistor, power will be dissipated in the form of heat loss. As we know, that heat loss or power dissipated by the resistance will not be useful for us, and this loss is called the winding loss or copper loss. Hope it is clear for you. And whenever armature currents flow through the armature winding, a loss will be occurring, that is called Ia square Ra, armature current square into armature resistance. Similarly, whenever field current flows through my field winding loss will be occurring, that is If square into Rf. And winding loss will always depend on the loading, and especially this armature winding loss Ia square Ra. Whenever we vary the load connected to my machine, Ia also varies. So Ia square Ra is always variable loss, whereas the field winding loss depends on the type of machine. For example, for shunt wound machine, in that case, field winding or shunt field winding current will be constant. So the field winding loss in the case of DC shunt machine will be constant because If is always constant irrespective of the load. So field winding loss is constant for a DC shunt machine. Whereas for DC series machine, whenever we vary the load current, load current varies, so armature current varies. Since the armature winding and field winding are connected in series for a series machine, If also varies with the load. So field winding loss is variable loss for DC series machine. And hope it is clear for you. Now let us move on to mechanical loss. There are mainly two types of mechanical losses: frictional loss or air friction loss. Frictional loss occurs at the bearings as well as in the commutator brush combination. And windage loss or air friction loss. whenever my armature is rotating, there will be air friction against the motion of my armature, and that causes air friction loss or windage loss. And let us have a look on some important notes. The sum of magnetic loss means iron loss. The sum of iron loss and the mechanical loss together, it is called a stray loss. And some of the problems you may see that stray loss will be given. So we should know that stray loss is equal to sum of magnetic loss plus mechanical loss. The stray losses are also called rotational losses. Why? Mechanical loss, obviously, it will be occurring only when the armature is rotating or when the armature is connected to my mechanical load, there will be a mechanical loss. Then how magnetic loss is considered as rotational loss? Because the magnetic loss or iron loss occur only when my armature is rotating. Only if armature is rotating, hysteresis and eddy current loss will occur in my machine. So magnetic loss is also considered as rotational loss. And I said before that core loss or iron loss or magnetic loss will be a constant loss since it depends on voltage. So and also mechanical loss will be also considered as a constant loss. So the entire stray loss will be a constant loss. But as I said before, copper loss always depends on the load current, especially the armature winding loss. Armature copper loss depends on the load current, and field copper loss uh, are independent of load current in the case of DC shunt machine, and field current loss depend on the load current on in the case of DC series machine. And all those points are already discussed. And in general, total loss of a DC machine can be written as sum of constant loss plus variable loss, and constant loss is WC plus variable loss means copper loss. To be precise, in case of DC shunt machine, variable loss means only armature copper loss. In case of DC series machine, variable loss means it is a combination of armature copper loss and field copper loss. Hope it is clear. Now let us discuss the condition for maximum efficiency in a DC machine. Whether it is DC generator or DC motor, the condition for maximum efficiency is same. So to derive the condition for maximum efficiency, let us consider a DC shunt generator. The output of a generator is V into IL, that is terminal voltage into load current. Then generator input will be output plus losses, where output is VIL plus losses means constant loss plus variable loss. Here the variable loss is IA square RA for DC shunt generator, and the constant losses are core loss, mechanical loss, and field winding loss will be constant for my DC shunt generator. So here IA can be replaced as IL plus ISH. So V into IL plus IL ISH the whole square into RA plus WC, where WC is the constant losses. And comparing to IL, the value of ISH is very small that we can neglect ISH, and let us consider IL is approximately equal to IA. Then generator input is equal to VIL plus IL square RA plus WC. Okay, we know that efficiency is equal to output by input. We know output is equal to V into IL divided by input means VIL plus IL square RA plus WC. And to obtain condition for maximum efficiency, consider the variable in this equation, which is the only variable IL. So differentiate this equation with respect to IL and equate it to 0. Then d eta by DIL is equated to 0. Then taking derivative, we consider division rule. Then numerator into derivative of denominator into derivative of numerator minus numerator into derivative of denominator whole by denominator square. Then VIL plus IL square RA plus WC into derivative of VIL is V minus V into IL into derivative of the denominator term, that is V plus 2IL RA plus 0. Then whole divided by denominator square. Whole is equated to 0. Then what we will get is VIL plus IL square RA plus WC into V equal to VIL into V plus 2IL RA. V cancelled, then VIL plus IL square RA plus WC equals VIL plus 2IL square RA. That means VIL and VIL get cancelled. Then what we get? WC is equal to IL square RA. That means constant loss is equal to copper loss. Constant loss. That constant loss should be having core loss, then mechanical loss and field winding loss for in the case of DC shunt machine. So we can conclude that constant loss will be equal to copper loss, or constant loss will be equal to variable loss. That is the condition for maximum efficiency. Constant loss is equal to variable loss. Now let us move on to the power stages of DC machines. First let us look on the power stages of DC generator. As we know, in the case of DC generator, the basic principle is when a conductor is moved in a magnetic field, an EMF is induced in the conductor due to change in flux linkage. So we want to rotate my armature, which is kept in the magnetic field. So in order to move the armature in the magnetic field, what we will do? We will use a prime mover to rotate my armature. So we give a mechanical power to my DC generator and we get electrical power from the DC generator. Okay, and by applying mechanical power to my DC generator, that is the mechanical power input, that is the input to my DC generator, and this mechanical power input means what? That is the output of the driving engine. Driving engine means the prime mover that we used. Okay, then what happens? My armature starts rotating. When my armature starts rotating, what all losses it will come across? One is frictional loss, that is the mechanical loss. Both frictional loss and windage loss will be occurring. Along with that, what is the another loss? Iron loss. Why? Both hysteresis and eddy current loss will occur when my armature core is rotating in the magnetic field. So when we give a mechanical input, my DC generator, my armature starts rotating, then it will come across the losses called iron losses as well as mechanical losses. Then a part of the mechanical power input has been wasted as iron loss and frictional loss. The remaining power will be obtained in the armature, that is Eg into Ia. EMF is induced in the armature, and when electrical load is connected to my armature, it draws current from the armature. So what is the power across my armature? That is generated EMF into armature current. Eg into Ia is the electrical power developed in the armature. Okay, when current is flowing through my armature winding, then what happens? Definitely Ia square Ra loss will be occurring both in field winding as well as in armature winding. That is the copper loss. Eg into Ia is the power developed in my armature, and after the copper loss we get the electrical power output from my generator, that is V into IL. Terminal voltage into load current, that is the electrical power output we obtain from my DC generator. What VA is equal to what? Eg into Ia, that is power developed in the armature minus copper loss. Hope it is clear for you. Now there are some other terms. Mechanical efficiency means total watts generated in the armature by mechanical power supplied. From the name itself, mechanical efficiency, it is clear that when I give a mechanical input, my machine, a part of power will be developed in the machine, that is in the armature, that is Eg into Ia is developed due to the application of my mechanical power. So the efficiency, mechanical efficiency is given as Eg into Ia, power developed in the armature, divided by mechanical power input. What is the mechanical power input? That is the output of my prime mover. Clear? So mechanical efficiency is equal to Eg into Ia divided by output of driving engine. Then what is electrical efficiency? That is watts available in load circuit by total watts generator. That is, even though Eg into Ia power is developed in the armature, we will not get the entire power developed in the armature across my terminals because there will be a copper loss. So the efficiency is showing the electrical power output from the DC generator to the electrical power developed in the armature. That is VI divided by Eg into Ia gives the electrical efficiency. Then what is overall or commercial efficiency of DC generator? When a mechanical input is given to my DC generator, finally an electric power output will be obtained from the terminals of DC generator. So the main output to the main input, that is the overall or commercial efficiency of my DC generator. So commercial efficiency is equal to what's available in the load circuit divided by mechanical power supplied. Hope it is clear for you. And for good generators, generally there will be an efficiency around 95% also, it will be available. And the relation between these three efficiencies is commercial efficiency is equal to mechanical efficiency into electrical efficiency. You can multiply mechanical efficiency into electrical efficiency, then EGIA terms will be cancelling out, then you will get that commercial efficiency will be equal to watts available in load circuit divided by mechanical power supplied or output of driving engine. Hope it is clear for you. Then let us look on the power stages in a DC motor. As we know, the basic principle is when a current carrying conductor is placed in a magnetic field, it experiences a force called a Lorentz force. Thus, my armature rotates. Similarly, in case of DC motor, we give a supply to my field winding to generate to produce magnetic field, and we give electric supply, DC supply to my armature windings also, so that we can say that current carrying armature conductors are placed in a magnetic field, then it experiences a force called a Lorentz force, or when it experiences a torque and it starts rotating. And that is the basic working principle of DC motor. Then we get a mechanical output from my DC motor when I give electrical input to my DC motor. So motor input is V into I. That means DC supply V is given across my armature. Then I will be flowing to my armature, and it is split as armature current and field current. That is the motor input. When we give motor input, that is electrical input, what happens? Current flows through my windings. Then copper loss will occur. After the copper loss, remaining power will be developed in the armature. That is mechanical power developed by the armature. Its electrical equivalent is EB into IA, back EMF generated in the armature into current flowing through the armature. That is EB into IA is the equivalent to the mechanical power developed by the armature. Then when it develop mechanical power, if I connect my mechanical load to my armature through shaft, what happens? There will be mechanical loss when it is connected to the shaft. When I connect my armature to my shaft, what happens? There will be mechanical loss called frictional loss. Also there are bearing loss also. Then along with the mechanical loss, which loss will also occur? Iron loss or core loss. Why? Both hysteresis and eddy current loss occur when my armature core is rotating in the magnetic field. Now my armature starts rotating in the magnetic field, so obviously there will be iron loss. So after armature power is developed, there will be iron and friction loss occurring. After this iron and mechanical loss, we get the motor output at the shaft. So motor output is also called shaft output. Okay, hope it is clear for you. And here also we have three types of efficiencies: commercial efficiency, electrical efficiency, and a mechanical efficiency. Commercial efficiency equals C by A. C by A means motor output by motor input. That is the final output from my motor to the main input to the motor. That is motor output in watts divided by VI gives the commercial efficiency. What is the electrical efficiency? B by A. That is when I give a VI power to my armature or to my motor, a power will be developed in the armature equivalent to the mechanical power developed in the armature. That is EB into IA. So what is the electrical efficiency? This electrical part divided by this electrical part, that is EB into IA divided by V into I, that is the electrical efficiency. And mechanical efficiency is C by B, that is motor output taken from the shaft to the mechanical output developed in the armature. Mechanical output taken out from the shaft side to the mechanical output generated in the armature. Its equivalent value is EB into IA. So what is the mechanical efficiency? Motor output in watts to the EB into IA. Hope it is clear for you, and from the figure itself it is clear. A minus B, that is when I apply a motor input my machine, copper loss will be occurring and we get EB into IA. So VI minus EB into IA will give us copper loss. Similarly, a mechanical power will be developed in the armature. When it is connected to the shaft, there will be mechanical loss as well as iron loss. So B minus C will give the sum of iron and mechanical losses. Hope it is clear for you. And if you have any doubt in this session or any queries, you may ask through the comment box or can mail me in the given mail ID. Thank you. That's all for today's session, and let us see on the next session. Thank you.